Thank you so much for joining, for your kind attention and participation. With this, I will like to conclude my talk. So, use of science for constructive purpose is very important. I wish a grand success to the conference and hope it will be really helpful for the interested students and researchers. Thank you, one and all.
Thank you so much, sir. Now I request to Dr. M.M. Karanskar, sir, organizing secretary of this conference, to introduce today's chief guest, Professor P.S. Patil, sir, Pro Vice Chancellor, Shivaji University, Kolhapur.
Good morning, all of you. First of all, I welcome all resource persons as well as the chief guest of today's function, Professor Dr. Pramod S. Patil. At present, he is the Pro Vice Chancellor, Shivaji University, Kolhapur. He did his MSc from Shivaji University in 1986, PhD from Shivaji University in 1990. He is working as a professor in Department of Physics in Shivaji University, Kolhapur since 1990. Now, I'm very happy to say here that he is one of the top 10 knowledge producer in India by careers in 360 ranking in the year 2018. Now, he is ranked in the world top 2 scientists by Stanford University, USA 2020. He is the Outstanding Research Faculty Award by Careers 360 ranking in India. He is the ex-coordinator of Department of Energy and Technology. He is the former coordinator, director of School of Nanoscience and Technology. He is the former head Department of Physics. He is the former director of IQAC, Shivaji University, Kolhapur. And I'm very happy to say that such a big personality with us. He has produced 45 PhD and 6 MPhil students. At present, 5 PhD students are currently working under his guidance. He's published more than 510 research papers in the international and national journals of well-reputed and 600 abstracts of national and international conferences. Now, total citations for papers is 22,697. Total citations, remember that, for the papers, 22,697. So its H index is 78 and ITEX index is 424. Now, this indicates how his role in a research area. Now, his research gate RG reads 1,45,600 RG and RG score is 48.15. Now, total research papers used by Mendel is 4,75,668. Now, these figures indicates how he involves in his research area in different, that is nanosciences, nanodevices, material science, and etc. He's written 4 books, 6 book chapters, and 1 Korean and 3 Indian patents. And at present, he submitted 1 patent. He is the recipient of prestigious Germanium Academic Exchange Service, that is DARE Fellowship Award in 1996 and 1998 at Fraunhofer Institute, Berlin, Germany. He is also a recipient of prestigious Brain Pool Fellowship Award of South Korea 2005 to 2006, Seoul National University, South Korea. He is the fellow member of Institute of Physics, London, UK. He is the life member of National Academy of Sciences, India. He is the fellow of Maharashtra Academy of Sciences, November 2013. He is the member of World Class QS Ranking Intelligent Unit. He is the member of quarterly Franklin membership, that is ID number is JA61370. He is the recipient of prestigious Brain Pool Fellowship Award of South Korea 2012 and 2013, Cheonam National University, South Korea. He is the former Dean of Science and Engineering Faculty, Shivaji University, Kolhapur. He is the BIOS Chairman of Physics in Shivaji University, Kolhapur. As BIOS member of Physics of Sanjay Godawat University, Savitribai Phule Pune University, Solapur University, Bamu University Aurangabad, and this is at university. He is the member of Governing Council Walchand College Sangli and the member of UJC New Delhi Committee to give autonomous status to different colleges. He get Best Microscopy Image in the World Award in 2010 in Nano Today, elsewhere publications in February 10, 11 and 2013. And remember that the impact factor of this Nano Today is 17.68. Now, Best Cover Image Award for Materials Today in the 2011, 2012, 2013, and its impact factor is 21.79. Now, this impact factor and its publications and award image indicates that how his role in nanoscience, nanodevices, and material sciences. He is the life member of several academic bodies in India and also in the abroad. He is the coordinator of MOU between Shiva University and Universities of Ontario, Canada, and MOU between Shivaji University and National Dong Yu University, Taiwan. He is the participant in Indo-Japanese Joint Project in 2013 and Indo-Egypt program in 2017 and 2018. He is the visited in different countries to deliver his lectures, to perform his research activities like USA, Germany, France, Singapore, South Korea, Taiwan, and Japan. He is the referee for many international journals, including American Chemical Society, which is the topmost journal in the world. His research interest in world ranking in India ranking as per Scopus 2019. Now, world ranking in India ranking as per Scopus is electrochromism is ranked 8 in the world, and no one Indian scientist reaches up to his research. It is 8 in the world and first in India. It is very glad to us that such a personality with us for the chief guest for this today's function. For gas sensors, he is the rank 3rd in the India for the year 2015 to 2020, and solar cells rank 3rd in India in 2010 to 2020. For the supercapacitors, he is the rank 4th in India 2010 in 2020. All this rank indicates that he is in between 10 in all over world and all over India regarding his research in electrochromism, gas sensors, solar cells, supercapacitors, as well as other material science research. He is the editor of International Journal of Material Science, Hinwani, Applied Surface Sciences Advances, elsewhere publishers. He is review editor, Frontlines in Material, May 2014. He is the International Research Project Reviewer of Pazzi Foundation, Israel government. He is the project evaluator, National Council of Science and Technology, Mexico government, Mexico. He is the international PhD reviewer, Cairo University, Egypt. He is the visiting professor of Cheonan National University, South Korea. His individual projects of worth rupees 4.75 crores. His Center for Nanofabrics has been funded by USA with 1.20 crores. DBT Builder funded project worth rupees 5 crores. Instrumental in common projects rupees 7.3 crores. Further, as I had read these projects in a course that is near about at present is as 25 crores. Now his Best Teacher Award 2014 in Shiva University, Kolhapur, and one of his best students received Best PhD Thesis in the world in the award 2014. That is Santamoy at present is working in South Korea. Now I'm very happy to all of you that such a big personality is with us as a chief guest for the today's function. So on the behalf of this international conference, behalf of this Vivekanand College Kolhapur, behalf of this our Swami Vivekanand Section Sanstha, I welcome Professor P.S. Patil sir and request him to deliver his invited speech for our students. and participants. Thank you, sir.
Thank you so much, sir. One of our resource person, Dr. Mustafa Bosta, has recently joined us. We welcome you, sir, on the behalf of our college and organizing committee. Now, I kindly request Honorable P.S. Patil, sir, Pro Vice Chancellor, Shivaji University, Kolhapur, Chief Guest of today's inaugural function, to deliver the keynote address. Please, sir. Sir, unmute. Please unmute your.
मॅडम तुमच्याकडनं अनम्यूट झालं.
Yes, sir.
आपल्याकडून अनम्यूट करा आपल्याकडून.
सर आपल्याकडून अनम्यूट होत नाहीये. पाटील सर तुमच्याकडून अनम्यूट करताय का? सर हे अनम्यूट होत कारण का सर आपल्याकडून अनम्यूट होत नाहीये. सरांना रिक्वेस्ट करा की त्यांचा माईक अनम्यूट करताय का म्हणून.
नाही
You can't unmute someone else.
into screen. कारंजकर सर
हा बोला, ऐकतो सर.
सरांनाच हे करा म्हणून सांगा, अनम्यूट करायला सांगा. इथनं होत नाहीये. तिने केले वाटतं.
एक कॉल करायला सांगतो.
कोणाला कोणाला
पाटील सर. एक मिनिट सांगा.
हॅलो सर.
हा
कारंजकर सर.
हा
एक कॉल करा की सरांना एक कॉल करा.
करा ना, कॉल करा.
इकडून अनम्यूट होत नाहीये सर.
असं काय झालं ते?
नाही, आपल्याकडून unmute
कॉल करू का
आहे.
त्याला? करा प्लीज कॉल करा.
सर करायला.
त्यांनी अनम्यूट करायला पाहिजे ना. हा ते नाही म्हणतात की सर.
माझ्या समोर हे अनम्यूट होत नाही करतायत ना.
हा
आपल्याकडे ही
मग त्यांना
झालं फोन चालू आहे.
फोन चालू आहे.
हे on करा.
हॅलो.
हा आता येते सर.
हा येतोय सर.
येस सर.
एक मिनिट.
येस सर.
येस सर.
हा 1 मिनिट.
येस सर.
हा
ओके सर.
ऐकू येते का?
ओके सर येते.
Yes, sir.
Okay,
Very
okay.
good.
Sorry, there was some problem with my laptop.
Okay sir, no problem.
I joined from my smartphone.
Yes sir.
Okay. Thank you very much. The president of today's function, Dr. Ramesh Ji Kumbar, principal of Vivekanand College, Kolhapur, my friend Dr. M.M. Karanskar, all the faculty members of the physics department, the very well-known resource persons, Professor Bosta from NRC Egypt, Cairo, Professor Ping from National Donghua University, Taiwan, and Professor Mangru from University of New South Wales, Australia, and my dear participant friends. I'm indeed very happy to be here on the occasion of inaugural function of this one-day international conference on nanoscience and nanodevices organized by Department of Physics and IQAC, Vivekanand College, Kolhapur. I know Vivekanand College is a very vibrant college with a lot of student-centric academic activities, and this activity is very important that you have today organized an international conference on a very hot topic of nanoscience and nanodevices. So initially, I would like to congratulate the entire team of Department of Physics for organizing this conference for the benefit of the participants in the jurisdiction of Shivaji University and many other participants from variety of universities in Maharashtra and India. I'm sure this conference will be very, very fruitful and rewarding to all the participants. This conference is online conference. However, there is a bit a limitation of interacting with the resource persons. But I'm sure that some of the students who are inquisitive in mind, they will ask some questions to the faculty members and resource persons from out of India. So international resource persons are there. You may interact with them through internet and through this particular conference. So this opportunity is very, very important. And I would like to congratulate the Vivekanand College, Kolhapur. So since I know that my time is limited, I have only half an hour. I would like to talk a little bit on smart materials. My friend Mustafa is here. Sir, hopefully you're all well amidst COVID-19. I'm very happy to see you here on the
Me too.
online conference.
Okay, me too. But a problem, I have a problem in my camera, so I solve it now. So I see myself and I see everybody. So I say good morning, everybody, and
Yeah,
welcome.
yeah.
Okay,
Good morning, sir.
please.
Yeah, nice meeting you.
Yes.
Yes. So today I'm going to talk on smart materials. And as we know, some of the materials which are called as the smart materials, they exhibit change in the properties. As Dr. Karanskar was telling, that at the nanoscale, most of the properties of the materials change. Electrical, mechanical, chemical, optical, and thermal properties of the materials will change at the nanoscale. And the smart materials are also the materials which exhibit change in their properties in a controlled fashion by applying some external stimuli. The external stimuli means the temperature or moisture or pH, electric fields, light energy, or chemical compounds. If we apply some sort of external stimulus to the materials, the optical properties of the materials will change. And those properties are recoverable. They can attain the original state once we reverse the external stimuli. So I'm going to talk on different aspects of these materials. Unfortunately, I cannot show you some of the slides which are there on my laptop. Now I have logged in from my smartphone, so that was the problem. Anyway, so the first device that I'm going to talk to you about is electrochromic smart window materials. The smart window materials are very, very important for the country like Egypt and India because you can control the optical properties of those materials just by applying a voltage less than 1 volt. So if the sun is too hot, you can apply the voltage, the transparent material can become blue or deep blue in the color. So you can avoid the very hot sunshine from the outside, and you can control the incoming light just by controlling the applied voltage that can be applied to the smart windows. So this is the way in which you can control the light by using smart coatings. And during nighttime, you can reverse the polarity of the applied voltage. The material becomes transparent and it is very, what can I say? It is like a comfortable situation. So this is very important material. So during daytime, if you apply some voltage, it becomes blue. And during nighttime, if you apply the reverse polarity, it becomes transparent. So these these materials can change the optical properties. In one stage, it is transparent. In other stage, it is deep blue in color. So this particular material is called as the electrochromic smart window material because it is changing the color. Okay. So there is one material called as a tungsten oxide, which can exhibit the change in color from transparent to blue. But there are many other colors. You can choose the material and you can select the color of the material. So, for example, there is another material which is called as a nickel oxide. If we nickel oxide in its native state, it is a transparent. However, if I apply voltage, it becomes blackish gray in color. So, depending on the material, you can choose the color of the material. Okay. So, there are several materials which are called as anodic electrochromic materials and cathodic electrochromic materials. Those materials are very, very easy to synthesize. In our laboratory, we have synthesized these materials to a larger extent by using the simple chemical methods. And like a tungsten oxide, molybdenum oxide, nickel oxide, vanadium pentoxide, and many other oxide materials we have selected, we have synthesized by using chemical techniques like hydrothermal, spray pyrolysis, and many other chemical techniques, with the help of which you can really have a wonderful coating of these materials on the ITO substrate. And then this substrate or this particular electrode is prepared. In order to fabricate the device, you have to make a device by using this material. Then another counter electrode material is required. And then you also need an electrolyte which can supply ions into the material. So when we apply the voltage, suppose my electrolyte is containing H plus ions or lithium plus ions, those ions intercalate into the material. And those intercalation of the materials will bring about the change in the color. For example, if I have tungsten oxide, it is a transparent. But if I apply the voltage, H plus or lithium plus ions start intercalating into the tungsten oxide host lattice. And therefore, the composition of the tungsten oxide changes from WO3 to HXWO3. X is the amount of H plus ions which are intercalated into the tungsten oxide host matrix. And because of the conversion of tungsten oxide into HXWO3, the change in color is exhibited. So change in color is only because of intercalation of H ions or lithium ions into tungsten oxide. We have to select the materials so that the materials exhibit some sort of conduits for the flow of these, for the intercalation of these small ions into them. And tungsten oxide is a material which can have inherently these conduits for the intercalation of small ions like a proton, that is H plus or lithium plus. And then once those intercalations are taking place, the material which is transparent becomes blue or deep blue in the color. And when we reverse the polarity of the applied voltage, whatever the intercalated ions are there inside the host lattice of tungsten oxide, they will start de-intercalating from the tungsten oxide. So from HXWO3, again we can recover WO3 by de-intercalating H plus and lithium plus from the tungsten oxide lattice. And thereby we get the original material which was there, that is a tungsten oxide. So it is between the switching of WO3 to HXWO3 and HXWO3 to WO3. And this particular cycle, this is one cycle of coloration and bleaching. Just like our mobile phones, they have lithium batteries. They also have charging, discharging cycles. Similarly, in the smart materials, we also have coloration and bleaching cycles. And you can, more are the cycles, better is the stability of the materials. And therefore, in order to fabricate very stable device, you need very good material which can withstand for about 10⁵ coloration bleaching cycles. Then that particular material or the device that can withstand for a particular building, if I apply that particular window material and the building material, that building will have the window which can last for about 5 to 10 years. So you need not have to change it because of the stability. So stability is one of the important factor, which is very, very important as far as smart window materials are concerned, as far as electrochromism is concerned. There are several buildings in the developed countries like America and other countries where most of the multi-storied buildings, they have been fitted with the electrochromic smart windows. And these windows not only change the color, but they can also substantially save the electrical energy because these window coatings, they reflect infrared radiations, and infrared radiations are responsible for heating of the building. So now in Kolhapur or in India, we are facing a hot sunny season. So in this particular hot season, the sunlight directly enters from our window and our building gets hot. But if I use this tungsten oxide material, it can reflect the radiation. Hello. Madam, सगळ्यांना जरा म्यूट करायला सांगा. Am I audible?
Yes, sir. It is audible, sir.
Okay, there was some problem in between.
Yes, sir.
Anyway, so I'm talking about these tungsten oxide materials, and like tungsten oxide, you can select many materials which are there. You can synthesize those materials, and characterization of the materials is also very, very important. If the material is a nanomaterial, then the efficiency of coloration is tremendously high, and you can have these materials viable for the buildings and houses. So these electrochromic smart materials are useful for the energy saving, and in most of the countries, we need to utilize these electrochromic smart windows. In India, as far as India is concerned, we have very hot sun. We need to switch on the air conditioners everywhere. However, if we fit our building with the smart windows, then it is possible to reduce the electrical energy for cooling of the buildings. Cooling of the buildings is one of the important way that you can save the electrical energy. So simply with the help of smart windows, you can save a lot of energy. So therefore, it is called as a energy conservation material. The material, with the help of this, you can conserve a lot of energy. So these are also devices which are very, very difficult to fabricate. And therefore, in India, there is some challenge. There are some bottlenecks in order to fabricate the device and commercialize the device in the market. However, there are several companies in America and abroad which have brought these devices in the market. However, there is not a single company in India which can fabricate these type of devices and market them into the Indian country and many other countries. So because there are some bottlenecks to be broken, it is very, very important that we have to fabricate the device which has a very large stability and which has a very large efficiency. However, if I use nanomaterials, we can fabricate efficient devices. However, the stability is a problem. The problem of the stability comes from the liquid electrolyte, because as I told you, the electrolyte is necessary to supply the ions like H plus and lithium plus, and this liquid will degrade the material. And therefore, a lot of research is going on into finding out the proper and stable electrolyte, from liquid electrolyte to solid electrolyte or semi-solid gel-like electrolytes. So a lot of research is currently going on in the field of gel electrolytes and solid electrolytes so that one can increase the stability of the material. If I look at the optical properties of the material, when it is in the transparent stage, the device exhibit around 90% transparency. And if I apply the voltage, the color change is observed and the transmittance goes from 90% to about 20%. So you can see the delta alpha, that is a change in the absorption coefficient of the material, is about 60 to 70%. And this is very, very important in order to save a lot of electrical energy. The country like Egypt or the country like India, we need such type of devices and we need such type of indigenously developed devices. So there is a need to develop those devices, and those devices can be developed through research. And therefore, in Shivaji University, we are doing a lot of research in the field of electrochromic materials. My student, who is now working as a professor, assistant professor in Krishna College, Mahavidyalaya, uh, Karad, is also one of the experts in India. He has also developed several materials for the smart windows. These are the inorganic materials, but there are several organic materials, several polymers. They can also be useful in the fabrication of the smart materials or smart windows. We are also working in that particular line, that how to utilize various polymers in the smart window applications. And we are collaborating with National Chemical Laboratory Pune for these particular applications. Another material or another device which are based on the nanomaterials that we have started is smart textile, or you can say the nano textile material. Since in and around Kolhapur, we have several textile industries, and therefore we have collaborated with those industries and institutions which are good in textile industry, which are good in research in textile. We got a center of excellence in smart textile, in which you can modify the property of the textile material. The Giza cotton is very, very famous. Giza is in Egypt. So Professor Mustafa will tell you the quality of the Giza cotton is very good, which is also famous in India. Khadi is also famous in India because it is an Indian product. So you can take a Giza cotton, you can take a Khadi, or you can take any other textile material. You can change the property of the textile material by coating the nanomaterials onto those textiles. We have established Center of Excellence by RUSA, and we have converted the textile material, a simple textile material or a fabric, into a smart fabrics or into a nano fabric. So currently, the textile material absorb water. This is the property of the textile material, that it absorbs water. However, we can repel the water by applying some nano coating onto the textile. So the nano coatings we have applied onto the textile are zinc oxide and titanium oxide. Those are super hydrophobic materials, and those super hydrophobic materials are synthesized and they are applied onto the textile material, so that rather than absorbing the water, it repels the water like a lotus leaf. And therefore, those textile materials or the fabrics are very, very important, and we can change the properties of the textile material just by applying some nano materials or nano coatings onto it. However, again, the problem is that if I wash the shirt or if I wash the fabric, it is necessary that the coating should withstand. It should not wash away. And therefore, the stability of those coatings against washing cycle is very, very important. However, we have done a lot of experiments in our laboratory, and we have come up to say 50 to 100 washing cycles. Suppose if I take a shirt and apply nano coating onto it, it will exhibit a super hydrophobic property. It will repel water. Not only that, it will also repel many other liquids like tea or coffee. Therefore, it is also stain free. So Not only that, we can also fabricate textile as a odor free. The odor is because of the sweat. It will not absorb the sweat into the textile materials. Therefore, you can have a odor free fabric. So all these important properties can be added into the fabric material just by changing the nanomaterials. So zinc oxide and titanium oxides are added to impart the superhydrophobic property into that, and therefore it is a wonderful material. We are collaborating with the DKT Institute, in which they are supplying pre fabric, which is not finished product, and we are applying the zinc oxide and titanium oxide nano coatings onto those. There are different methods. Once we prepare or we synthesize zinc oxide powder, and then ex situ coating of these zinc oxide nanoparticles onto the fabric is done. In the second part, we do synthesis as well as application of those nanoparticles on the textile in one step. And for that, we have a special technique which is called as a Bessel ultrasonic technique, which is available. We have this particular technique in our lab, and this is the only instrument that we have in India. And this is a special instrument that we have. With the help of that instrument, we can fabricate the nanoparticles, and we will apply some sonochemical techniques so that those particles are incorporated into the textile material. So synthesis and incorporation take place in one step. That will lower down the cost of the material and the cost of the fabric, and therefore we are doing a lot of experiment in the field of functional textiles. Not only that, we all have already experienced the COVID-19 pandemic. During pandemic, we have understood the importance of bacteria and viruses. We can also coat the fabric with antibacterial coatings, antibacterial materials, or antiviral materials. We have so far coated the textile materials with antibacterial zinc oxide material and many other material like silica. So these coating materials can be applied to the textile so that the textile can kill the bacteria, or the textile material can kill the viruses. Not only that, we have also synthesized some copper oxide material nanoparticles, and we have incorporated that copper oxide nanoparticles into the mask. So the mask becomes very efficient in killing the bacteria and the viruses. It can also kill the coronavirus. And therefore, this is a simple technique to remain away from the COVID-19 infection, or many other infections are there currently in the atmosphere. So you can avoid those particular infections just by wearing a mask which has antiviral coating. And these antiviral and antibacterial coatings can be imparted just by applying or incorporating several nanoparticles into it. And our lab is expert in incorporating several nanoparticles into the mask. Mask is of course a fabric, or it is a textile material. So we can incorporate any nanomaterials into the textile material. That particular technology has been developed in our laboratory. We also have the foundry industry in Kolhapur. There are several largest foundry cluster in Asia that is available in Kolhapur. And that requires also some functional materials which can withstand the temperature about 1300 or 1400 degrees Celsius, because they are dealing with the metallurgy, they are dealing with the stainless steel or aluminum product. And we have also developed some coatings which can withstand a very high temperature of about 1300 and 1400. And we have transferred that technology recently to one foundry, Seraflex Industry in Kolhapur. And that particular aspect has also helped people in and around Kolhapur to develop the industrial nano coatings into that. So these are some of the materials that we are working at Shivaji University Kolhapur in our nanotechnology department's lab. And I'm sure that there are many other applications. You will listen to Professor Bosta is a very famous scientist in the field of solar cells, and he will talk about solar cells and other energy harvesting materials. And definitely, they are doing wonderful work. He also has established a lot of interactions and collaborations with the international scientists abroad. We also have collaboration, and we are also developing one material called as the CJTS. He will throw some light on solar cell materials. Professor Mengro from University of New South Wales, Australia, is also a very well-known researcher in the field of perovskite solar cells, and I'm sure that he will throw some light on energy conversion or solar cells devices which are based on the perovskite coatings. Perovskite is a recently acquired a lot of importance, and because it has exhibited efficiency as I think efficiency equal to that of the silicon. So it has a potential of replacing silicon solar cell, and therefore his lecture will be very, very important. Professor Peng from National Donghua University is very special scientist and specialist in the spectroscopy, and he has a wonderful technique in his lab, and I'm sure that he will exhibit all these technologies for the today's participants. And therefore this conference will definitely will be very, very fruitful. I request all the participants to take part actively into this conference. You also can take notes, and some of the concepts are very, very important today. These four scientists will tell you, and if you take out the notes, that will be very good guidance for you to take up research in your future career. So once again, I would like to stop because I have been given only 30 minutes. It is 10:32. So I would like to stop. And before I stop, I would like to thank on my own behalf. I would like to thank Professor Bosta, Professor Mengru, and Professor Peng for accepting our kind invitation to remain present in an online mode. Only even though there is some gap of time lag is there, in India, it is just 10:30 a.m. I'm sure in Egypt it is a morning, early morning probably, and so the different time zones are there, and these all the three scientists have kindly consented and accepted our kind invitation in spite of the different time zones. It is I don't know whether it is convenient to them, but in spite of this inconvenience, because of our association with them, they have accepted to be a part of this international conference, and this conference is already a successful because they have accepted our invitation, and it will be successful because of their very intelligent talks that we will see in after my talk. So I once again congratulate the entire team of Vivekanand College Kolhapur for organizing this international conference for the benefit of the student. Thank you so much.
Thank you so much, sir. Professor P.S. Patil, sir, is our eminent member of Board of Studies of Physics Department. While we are organizing such events, Patil sir always stood behind us as a backbone. So thank you so much. Now I kindly request Honorable Dr. R.R. Kumar sir, Principal of our college, to add presidential remark over this inaugural function.
Hello. Am I audible? Hello.
Yes, sir, it is
Okay.
audible. It is audible.
Okay. Namaskar. Vivekanand College Kolhapur. In this Vivekanand College Kolhapur, today we have organized International E-Conference on Emerging Trends in Nanoscience and Nanodevices. Just now, our Pro-Vice Chancellor, Professor Dr. P.S. Patil, has given keynote address. Though I am not from the physics, I know these words, that is what you mean by nanoscience and nanodevices. My curiosity is increased regarding the nanodevices. As you know, the Vivekanand College Kolhapur, it was established in 1964 by Sri Swami Vivekanand Shikshan Sanstha, founded by Shikshan Maharishi Dr. Bapuji Salunkhe with the motto, Education for Knowledge, Science and Culture. And college always organizes such events. Today, I am very happy because for this conference, along with our Pro-Vice Chancellor, we have 3 international scientists, Professor Payne, Professor Mangro and Professor Mustafa. I welcome you all as a principal of this college. Sir, the college is reaccredited by NAC with the CGPA 3.24, that is A grade, and University Grant Commission has given potential for excellence twice to the college. Also, college is recognized as DBG Star College. In Shivaji University Kolhapur, college have academic, sports and cultural excellence. Department of Physics is one of the premier departments of this college. The department has research linkages with Department of Physics, Shivaji University Kolhapur, and the School of Nanoscience and Technology, Shivaji University Kolhapur. More than 20 students of the department achieved merit ranks in Shivaji University Kolhapur. Besides of this, 24 students achieved Inspired Fellowship of Government of Maharashtra. As a principal of this college, I am very happy and also extend a warm welcome to all the speakers, delegates, all resource persons present for this today's function. I am very happy to see that Department of Physics along with the IQAC is going to organize such type of international conferences in future also. With these words, I definitely say that this conference is very helpful to all young researchers in the field of nanosciences, because as we all know, today's world is called as a nano world. I wish all the success to this online international conference. Thank you. Jai Hind, Jai Maharashtra. Thank you.
Thank you so much, sir. Our honorable principal always stood behind us to organize such events which are student-centric, which are research-centric. Thank you so much, sir. We have come to the end of this fabulous inaugural function of First International E-Conference on Emerging Trends in Nanoscience and Nanodevices. For the last but not the least act to propose vote of thanks, I request Professor S. Sir.
Now I'm here to propose vote of thanks of today's international conference on behalf of Vivekanand College, IQAC, Vivekanand College, Kolhapur, and Department of Physics, Vivekanand College, Kolhapur. It's our prime duty to express our heartiest gratitude for Honorable President of our Mother Institute, Abhay Kumar Salunkhe sir, and Honorable Secretary Shivangitai Gaude of our Mother Institute. Now I would like to admire Professor Dr. P.S. Patil sir, Pro-Vice Chancellor, Shivaji University, Kolhapur, for delivering very fruitful and knowledgeable keynote address, which is very beneficial for all of us. Also, we all are very much thankful to all eminent resource persons who are joined virtually with us in very sharp timing. even though there is a time lag between Indian timing and the time of their country. So I would like to express my heartiest gratitude for all resource persons. Without the support and inspiration of uh, honorable principal of the college, it is not possible for us to organize such nice events. So we all are very much thankful to our honorable principal for giving us such a nice opportunity to organize such a international conference. We express our sincere thanks to Dr. Shruti Joshi ma'am, the IQAC coordinator of Vivekanand College, as she always encouraged us to organize such academic activities which provide the very effective platform for the students and also faculty to present their research at international level. I am also very much thankful to all participants and faculty to present their research at international level. I am also thankful to including organizing secretary, convener, co-convener. Without their hard work, this event was not possible. So I am very much thankful to all my colleagues of the department and even non-teaching staff of our department. Thank you one and all.
Thank you, sir. With the permission of President, I declare that this inaugural function is over. Before winding up, there is some announcement from organizing committee form which will be shared in Telegram group of conference at the end of the function. After successful submission of feedback form, the certificate will be generated on their registered email ID. Those parties in their registered email ID. And sorry for the interruption. And those participants will win the best poster presentation award, will also get their certificates on their registered email ID separately. After this inaugural function, we have 3 invited talks. The first invited talk that we will start on 11 a.m. The first invited talk will be delivered by Professor Weng Ping Peng, National Dongguo University, Taiwan. This session will be chaired by Professor S.V. Malgaonkar, sir. After this, we have a second invited talk at 11:50. That session, that invited talk will be delivered by Professor Mustafa Bosta from Department of National Research Center, Egypt. This session will be chaired by Professor C.J. Kamey, sir. And last, third invited talk will be delivered by Dr. Meng Rui from University of New South Wales, Sydney, Australia. Very shortly, we will start our first invited talk, 11 a.m.
Professor Karanskar.
सर हॅलो सर
Karanskar sir.
हा बोला सर
ते हे पेंग सर जॉईन आहेत काय?
हो जॉईन आहेत सर ऑल these are joined with for our inauguration function. So by the permission of
Okay sir, okay.
We will start instead of 11 o'clock, we will start at 10:50. 5 minutes are there.
Only halt is of only 5 minutes.
Yeah, only 5 minutes. As we mentioned in our
Yes.
program, it is 11, but we will take, that is the 5 minutes break.
Before 5.
So the schedule will move like 10 minutes in advance.
Professor Peng, can we audible?
Yeah, yeah.
So we'll start the session. Malokar sir, please start the session because he already shared his play.
So should we start? Can you hear me?
Can we start?
Sir, just give us 5 minutes. Peng sir, just give us 5 minutes.
Okay.
I request S.P. Malgaonkar sir to chair this session.
Okay, thank you. First, I would like to welcome Professor Dr. Wen Ping Peng, Department of Physics, National Dong Hao University, Taiwan. Dr. Wen Ping Peng from Taiwan is the first resource person for today's international conference. It's my responsibility today to introduce Dr. Wen Ping Peng. Briefly, because of the time restriction, I am going to introduce Dr. Peng sir in very short. He received his doctorate degree in physics in 2004 from National Taiwan University. He has developed a very sensitive charge detection device, which is most useful to detect the cancer cells. Another important instrument which he has developed is the ion landing instrument, which is very useful for studying catalytic reaction in gas phases. Most of his research work is focused on novel mass spectrometric methods, which are mostly used in rapid identification of viruses, bacteria, and cells. Another important work of Dr. Peng is that he and his assistants developed or he designed ion trap mass spectrometer, which is mostly very useful to measure the mass of sub-micron meter-sized particles. Recently, Dr. Peng and his group are going to work on rapid differentiation of nanoparticles. Mostly, his area of research work is focused on ion trap theory and instrumentation, pathogen identification using mass spectrometry techniques, electrospray mass spectral interpretation, detection of viral and bacterial particles, nanodiamond material for biomedical application. Other than this, Dr. Peng has published so many publications, papers in national and international journals. But because of time restriction, I am going to mention here some important papers which he has published at national and international levels. He has published a paper in Applied Nanomaterial Journal in 2021. The title of that paper is Oxidized Diamond Nanoparticles for Quantifying Immunoglobulin G Antibodies. One more paper which he has published in 2018 in Analytical Chemistry is on ionization of sub-micrometer sized particles by laser-induced radiofrequency plasma. In 2013, one more paper he has published is in Journal of American Society for Mass Spectrometry in 2017 was on high mass ion detection with charge detector coupled to rectilinear ion trap mass spectrometer. The analytic chemistry in 2011 is on interpreting the charge state assignment in electrochromic mass spectra of bioparticle. After this brief introduction, I very kindly request to Dr. Peng sir to start their talk. Thank you, sir.
Thank you for the chair's kind introduction, and also thanks for the invitation from Professor P.S. Patil. And I think it's long time like we don't have chance to visit Shivaji University. Like we have a couple of the colleagues there, and we know them quite well, and it's long time, which is quite important. I mean, the proteins, okay, is quite important for the diagnosis of many diseases. So today I'm focused on the point like to the point like which I am as a mass spectromist, I'm kind of curious about how to use mass spec technique to investigate those antibodies, especially we know the IgG and IgM, and how to do it quantification in very, very low concentration level. Here we target at a nanomolar concentration. How to quantify them accurately using mass spectrometry technique. So because of time, I think I choose like major two topics like recently we are doing. One is using diamond nanoparticles. We found using diamond nanoparticle, we can do the quantification of the antibody easily and mostly like straightforward, and also can be compatible to other techniques like gold nanoparticles. Besides of that, we recently developed a mass spectrometer we call megadalton linear unchecked mass spectrometer. And this technique is very useful. We can detect higher mass like hemoglobin N antibody. This mass is quite huge, around 1 million Dalton. So with this huge mass, it hardly can be detected using mass spectrometry technique. So we developed a technique, home-built mass spectrometer that is able to detect the hemoglobin G and as well as hemoglobin N at the median Dalton mass range. That is quite huge, and we got a success on this kind of instrument development. So mostly antibodies, we know there are a family of 5 of them, including the IgG, IgA, IgD, IgE, and IgM. As you can see, IgG is like they have a disulfide link, and they have exposed some active area and the not active area, as we will see later, and also IgM, like this joint molecule. If we want to detect those using mass spec, it will be very challenging, especially it's like in many techniques, like including the detection, is the major things, like how to detect them. Okay, the second thing is like how to quantify those molecules in solution phase. So because of this kind of antibodies, very important. For example, like dengue virus, like people try to detect IgM, and the COVID-19. Okay, people can detect IgG and IgM, and to judge is early infection or late infection. For example, like dengue virus infection in blood plasma, the author has shown like with their plasma surface, they are able to detect the dengue virus, and the methodology is compared to ELISA as to show the performance of this. So that means the detection of the IgM is quite important, as it can be a biomarker to identify the dengue virus infection. The same thing like for COVID-19 patients, people also using the IgG and IgM antibody detection. And this kind of detection also very important. And one of the major techniques, not only antigen detection, but also the antibody detection. And this kind of, besides the antibody treatment for the like COVID-19 disease patients, okay, so knowing the antibody quantity is very important. Which kind of species, like in human body, also very important too. As the chair say, like we recently, like last year, we developed using neo diamond, and we are able to quantify okay, this IgG first in antibody, and we achieved. I will explain this in detail, but not very detail. Okay, as you can see here, this is a lamina isosome, and we found based on the mass spectrometry signal, quantitation is possible using this kind of technique, and from this concentration we can estimate how many molecules were assault on top of the neodymium surface. Besides of that, we also can know, also can calculate how many IgG is on top of the nanoparticle. This is very important because, as we know, for drug delivery, right? How many drug, okay, can be carried on top of the nanoparticle delivery system is very important. So quantitation of the numbers of molecules can be absorbed on the diamond or nanoparticles is of great importance in the drug delivery study. So this is very important and very important step. Conventionally, we know people use fluorescence label. For example, gold particle, they can fluorescence label, but if we can use neodymium, it's without the need to label the specific dye molecule, right, on top of the your nanoparticles. So diamond particle itself already good enough for us as a nanoparticle can be used to quantify the number of molecules there. The second thing is like as we will prove later on, as you can see the graphic abstract here. Obviously, we prove in this paper. Okay, we have proven this in this study. The antibody is tail-on configuration. So we not only prove the quantification of the nanoparticle IgG molecule on the nanoparticle, but also we can show the configuration is tail-on using mass spec technique. I think this is quite novel, and also not only novel, I think it should be very useful, since we know if people want to define the protein antibody configuration on a nanoparticle, people use protein G or protein A as a linker or anchor to catch or to link with the antibody. Okay, so from this study, we know the diamond itself already can be a good antibody carrier and with tail-on configuration. This tail-on configuration is very important because this allows the Fab C active and can be used for the next applications. So this is very important, and of course, we know this is maybe very useful because without one step, right? You don't need to label, and you don't need to even, provide any kind of things. It's already there, and just one step, and you can directly use. So this greatly simplifies the sample preparation for the bioapplication part. So to investigate the system, we first try to compare the two systems. One is the high temperature and high pressure neodymium. As in figure B, the TEN is like a single crystal type neodymium. This quite usually were used for the neodymium or for the drug delivery system, or for the nanoparticle tracking system using the HPHT neodymium. But here in this study, we we found oxidized detonation neodymium. We get a sample initially from the sample A, and after doing the treatment, you just anneal the sample and raise the temperature to 450 degrees for 2 hours, and via the air oxidation, then you can prove like mostly it's a carboxylate oxidized DND can be produced in this case. So the TN shows the size of this, and the high temperature, high pressure diamond, they are very close related to the same scale. As we use the dynamic light scattering, the particle size, we measure the size is around both of the HPHT and the oxidized neodymium. They have a very close size. And also the zeta potential is minus 52 millivolts. So they are the same level, okay? Almost the same level. So it's a good system like for us to compare and to know what's the chemistry happens on the surface, on top of the neodymium. So we first characterize using the Raman, you know, SP2 and SP3. If you have an SP2, it's pure diamond peak, as the blue curve here in the figure D, and obviously this is pure diamond peak, okay, SP2. If you have SP3, like we call G band here, and obviously OSDND, oxidized diamond, and HPHT, single crystal, of course, pure diamond, right? So you expect to see the pure diamond peak here. About the functionality of the surface, as you can see in figure E, and obviously you can see as received diamond, okay, the feature is not here. But when we, after oxidation, as we say, like 2 hours, 450 Celsius, the functional group is somehow close to the HPHT diamond. Okay, you have a CO, OH, and CO bond, and the COC bond. Like that means functional group like COH is there. And we also do the we also perform the SPS analysis, and obviously HPHT neodymium have something like a carboxylate group COH, and also OSDND. Okay, after oxidation, we found we can enrich carboxylate group more, as you can see from the SPS, like a figure H. Okay, this is without treatment, and with treatment is obviously different. So we know the diamond what we have, and also then we can start to explore more simple characteristics. Like okay, we know the PET measurement. We know specific surface area. Obviously, OSDND is a factor of almost 5 higher, okay, 5 to 6 higher than the HPHT neodymium. Besides of that, we also can calculate the maximum absorption capacity of diamond and for different molecule. And supposedly because we know it's a carboxylate group, so we know COH size, okay, it's like 10 to for HPHT neodymium is around 1.95 times 10 to 14, okay, and the OSDND is around 1 to 1.5 times 10 to 15. And we also know the different configuration. If IgG antibody on top of it, how many of molecule can be here? Okay, we can estimate the number quantitatively. So before those are the above part, I guess we do the careful characterization of those diamond surface. Now we know if we can use the diamond nanoparticle. First of all, you can see here the signal intensity can be enhanced almost 2 order of magnitude at least. Okay, we can enhance the same signal. Okay, from 15 nanomolar and to very low, like a 10 nanomolar or even lower. Okay, so we can see the signal without and with nano diamond. With OSDND, the signal can be enhanced a lot. Okay, we can extend the detection limit to lower one. Besides the number of nano diamond concentration we found, there is an optimized condition around 10 microgram per mil ND have a highest strength signal. So we use this condition to explore our experimental condition. And to do the quantitation, we meet one thing very important, like as we have in multi-sample preparation, we did the homogeneity, control the sample homogeneity here. As you can see the figure B. The single crystal is microcrystal, okay? The size around, the crystal size around 5 micrometer. Okay, it's quite uniformly if compare the traditional sample preparation method. So the relative standard deviation can be reduced to like 18% for IgG signal, which is quite good, as you can see for the details in our previous publications in here. Okay, if you have interest for that. And then we know our signal is quite stable, so we can change the different concentration and observe, okay, the signal. Okay, the blue one is like we just like put diamond in and see the signal. Okay, the figure, as you can see here, the red one is like we do the second injection, like we after diamond injection, the residual solution, we use another nano diamond and inject again. We can still see the signal. That means at a higher concentration, in figure E, you start to see more signal. That means, okay, higher concentration, one diamond, the first diamond inject all the protein, but still have residue molecule, IgG molecule inside the solution. So we start to get signal. Okay, this is what we call second injection. So this is the technique using nano diamond. The advantage, you can do it multiple times. So you know how many molecules still left there according to your ion signal. So this is HPHT nano diamond. And for OSDND, we found the initial concentration is not 10 nanomolar, it's 4 nanomolar as compared to HPHT nano diamond. That means this can be extended to lower concentration using, it's not a strange, right? Because we already know from the BET measurement, the surface area is more as compared to HPHT nano diamond. So we know, okay, the lower detection limit can be down to 4 nanomolar, and also for 5 nanomolar, it can be increased to 35 nanomolar. And starting from 40 nanomolar, we start to see the signal for the second injection. Okay, so the signal here showing here is very stable and it can be repeatable and very easily. So we plot the lamina plot. Okay, then we fit the curve and the lamina isosome. And as you can see here, and for HPHT nano diamond is around 10 to 1.5, 10 to 13. Okay, and for particles, okay, you can observe for the linear C and D, the linear part of this lamina isosome. So we know the linear part of the lamina isosome is useful, right? So we can calculate how many, based on this curve, we can calculate how many particles will absorb and forming the monolayer, okay? And we also do the fitting lamina isosome model to fit this. Obviously, we see very clearly the concentration greater than 10 nanomolar. Okay, 10 nanomolar for HPHT was observed, and also it's also formed the multi-layer. How can we know this? Because we know when we fit this, it's kind of heterogeneous. This index N is 5.21. It's quite high. That means the heterogeneous surface. So we, from the mass spectrum signal, we know after 10 nanomolar, okay, after 10 here, 10 nanomolar, the signal still increasing. That means more IgG will absorb, starting from the second extraction, right? It still absorbs molecules. So that means from this mass spectral analysis, we already understand multi-layer formation on the HPHT neodymium. However, OSDND shows a different scenario because the monomer concentration we found is around 35 nanomolar from the linear fit. And we also used the laminar isolation fit, and we found 32 nanomolar. So from this fitting is quite in good agreement with each other. That means the IgG molecule on top of the OSDND is monolayer formation there. So it's quite interesting. The two different diamonds shows different association behavior here. And besides of that, we can calculate with different calculation from the IgG. Okay, we from this laminar isolation analysis, we know the OSDND here. We focus on OSDND. We know it's more layer formation. So the association property is much better than HPHT neodymium. Then we want to estimate, okay, how many, this kind of configuration is possible. It's a total, we know 6,000 and around 200 molecules. The maximum number of IgG on the OSDND. We estimate this number quite exact. Okay, we also estimate the IgG molecule if they are, assume the surface area is known. So we can calculate if psion is 9,900, around 10,000, right? And head on and tail on, and also flat on. So these two configuration is possible. So from this number, we already know the orientation of IgG on OSDND for monomer formation might be side on or tail on configuration. That's two possibilities. So in order to confirm it, okay, later on we will confirm it after this slide. We just compare, okay, the number we can analyze here as compared to other direct and indirect methodology. We found, okay, our estimate of the number can be comparable, not only comparable to other gold nanoparticle system or polystyrene bead or silver particle. We also found, because this is a reviewer, when they asked us, okay, can you check with Breffel assay, the indirect method? We found our measurement is consistent with others, like it's almost 3 times higher than our estimation. That means when people using like a Breffel assay, some kind of indirect method technology to measure the protein absorption on top of the nanoparticle, low 2 to 3, and we also confirm with this. Finally, I want to say like how to confirm this orientation. Okay, we use HCG, like a human chromic gonadotropin HCG molecule, and first of all we do the multi-analysis and found this around 1 micromolar concentration. Around 1 micromolar concentration, we can see the antibody antigen is here, over here. Okay, so we use the protein. This is a neomagnetic protein, figure B, and the figure D is a schematic for this. We use the magnetic bead with protein G, so we know it's tail-on configuration. As you compare to these two figures, mass spectrometry analysis, obviously you see the enlargement here, figure here. HCG signal is here. With neodymium, the HCG signal is quite good as compared to the magnetic bead. Because of this spectrum, we know the HCG mostly we cannot claim 100%, but I believe it's more than 90% or 80%. It's tail arm configuration on top of this. So we can simply conclude our gold nanoparticle system is very straightforward and simple, can be a simple antibody antigen platform, okay? And it's very useful, might be useful in immunodiagnosis part analysis. Okay, I still have 4 minutes left, and let me introduce another technique. We developed our homemade instrument. Recently, we make a progress detection of IgN at a nanomolar concentration. This is our setup. We use a thermal linear ion trap, okay, as our method analyzer, and we developed our own trap detector. It's very sensitive, can be with a noise about 200 electrons. So that means we can detect 200 ions if you have those kind of ions. And this whole system, I just let you know, conventional, like a thermal linear ion trap like this, the top one, the left-hand side one, okay, it can only scan to 4,000 mV. That's the detection limit. We also, in our lab previously, in the right-hand side here, we developed the retinal ion trap at that time. We can detect IgG marker, as you can see the previous antibody. We can see the signal. However, to using the void scan, as a commercial way did, we cannot detect higher mass than this one. So we use our own methodology and show like we can detect this IgG signal is quite good. And the spectral quality is as good as the multi-top commercial instrument. And I don't want to claim the detail here because time limit, but I can say we also extend, okay, the methodology. We can detect the thyroglobulin. Thyroglobulin, the mass-to charge molecular weight is around 330,000. Okay, 330,000, and we can see the signal is quite good. So how good of this we can compare with commercial top? This is in our lab. We have this multi-top, it's Bruker instrument, and the top one is our spectrum. The bottom one is we obtain the top one. The top has the upper limit, detection limit is 5,000. Okay, above the 5,000, you detect nothing because the detector is not functioning well. So as you compare the quality of our one and the commercial Bruker multi-top is microflash, we are not only comparable, actually it's also better in terms of mass resolution in this mass range. We also compare other technique like people use cryo detector, the left-hand side one, and they can detect the IgN here, okay? And the others, they also can, this is neomembrane detector. They can also detect like IgG and IgN. And this is Sumazu's Megatop. They change the detector, okay, detector. I don't want to tell about the details, but they use another detector, they can see the signal, okay? Now, how about Earth? We can detect a signal like this, okay? This is IgN signal. And we can reach 200 nanomolar. What does this mean? This means detection of IgN can reach 200 nanomolar, like 0.2 micromolar, which is better than above instruments. As I show you about the instrument, they're all greater than 0.5 micromolar. So that means using our homemade instruments, we have a better sensitivity than the commercial available system. And with the use of the neodiamond here, we found we can even enhance the signal and even to 5 nanomolar. So the charge signal is not invincible, but we can see double charge, okay, third charge, fourth charge, and fifth charge. So that means our methodology is quite sensitive and found can be better than other technique. For example, people use like a long fiber detection technique, and they can detect around 10 nanomolar, and we can be better than that. That's quite impressive also. So I think time is almost done, 30 minutes. as I can summarize what we have found, here we can detect IgG and IgN antibodies at a 5 nanomolar concentration using the neodiamond OSDMD. Okay, this is what our observation and our measurement. And the IgN mass spectrum we can acquire for the first time using linear ion trap system. This is found in the first time in the world. And also we can direct quantification of antibody using OSDMD with spectrometry technique for detection. So that means direct quantification, okay, not indirect. Okay, you be to be careful about this. This is direct quantification without okay sample preparation, without the dye labeling. We can do it directly. Okay. Finally, the orientation of the antibody is confirmed. Is most probably is tail on configuration. This is also first time we confirm for these things. Finally, I think I would like to thank for your attention. Okay. Thank you.
Thank you very much, sir. Now all participants are requested, if you have any doubts, queries, now the session is open for interaction. Please ask any queries, doubts in chat box. If you want, you can write your queries or doubts in chat box also. Raise the hand, Murukai. Unmute your mic and raise the hand if you have any doubts. Now the session is open for discussion, interaction. If
Yeah,
you have any doubts.
If you have any questions, welcome. And
yes, sir. Yeah. Participants are requested to ask any queries or doubts. Session is open for interaction.
so if no, then I am going to quit this. Okay. Probably is quite, different here for you.
If there is no any question.
So I have one question.
If there is no any question, can we conclude the session?
Hello, sir. Hello, sir.
Yeah, hello.
I have
Hello.
one question, sir. You have mentioned the different technique, that is a MALDI technique, matrix assisted laser desorption.
Yes.
What is this? That is a different technique. I heard first time.
Okay. Actually, MALDI technique is not new. That's Tanaka won the Nobel Prize in 2002 because of MALDI technique. Tanaka won the Nobel Prize. So MALDI technique actually is quite well known. Also in material analysis, people use it to characterize the gold nail particle. Okay, gold nail particle synthesis, and they use MALDI technique to analyze it. So it's already well known. But to do this, as you can see in our paper, you have to control the homogeneity of your sample, because conventional way, I didn't mention this because it's beyond this topic. I didn't put energy on top of this because most people using the dry droplet, the sample crystal mostly is inhomogeneous. So that's cause the signal is quite fluctuated and also have a sweet spot. And that hinders the analysis for the quantification, because your signal fluctuation is quite huge. Therefore, it is impossible for us, if you use dry droplet, the conventional people use methodology, you cannot do the quantitative analysis. So if you want to perform the quantitative analysis, then you have to use the way as we introduced, like a force droplet dry droplet, forced dry droplet method. We use a way easily to prepare the sample, and that sample can be with homogeneous from the microscope image. With the help of that technique, you can really introduce, the homogeneous sample preparation. Then direct quantification is possible. So if you can use with this technical quality, then the things will be very straightforward and very easy. As you can see here, our data quality, it actually is really straightforward things as in our lab.
Hello.
Hello. It's
Sir,
kind of
sir, any
interrupt.
interruption? Yes.
And now it's reconnected.
Hello, sir. I have one question.
Yeah. Hello. Yeah. You can.
What is? Hello, sir.
Yeah. Hello.
What is the basic concept and theory behind this ion trap? Hello.
You mean the ion trap?
Hello.
Hello. Yeah. Can you say it again?
Hello,
kind
sir.
Of yeah. Hello. Can you hear me? Wow. The internet is not stable. Hello? Hello? Can you hear me? Wow, interrupt.
I hear you. Yes.
Okay. Thank you.
Okay. Okay. Now you can speak, and I hear you. Maybe
Yeah,
there is a
I
problem with somebody,
I didn't
but it's
listen
okay.
to your questions clearly. Can you say it again? I mean,
Okay. You can ask you now.
I cannot hear. I can hear from you, Professor Rota, and but I cannot hear from Professor.
Yeah. Egypt, Taiwan. Yeah. I
Kind
hear
of
you
internet
clearly.
unstable. I don't know why.
Maybe.
But I can
some
hear you
problem.
clearly. Australia is.
Okay.
We have good connection. And not India. I don't know why.
Yes. Maybe India is a little bit far from Taiwan. Maybe.
Yeah, we have 8 hours flight. I know. Was to see me. No,
Yes.
8 hour flight.
Nice to meet you, and it is nice call and talk. Thank you for this information. And unfortunately, I am not interested in the biological materials, but I understand something from your call, from your talk. Thank you very much for that.
Yeah, thank you. Yeah, thank you. Thank you very much. Yeah. I think it should be their local internet thing.
Hello,
I
sir.
don't know. Yeah. Now I can hear you.
Hello.
Yeah. Hello. Yeah.
And sir, there is one question. There
Yes.
is one question from participants. Can we program nanoparticles to do complex operations in medical field?
Oh, yes. Okay. Actually, we do in the serological analysis. We really put in the RNA diamond in series. Okay. And we can really catch. I didn't show the data because this experiment is undergone. And actually, we can Okay. I think we can. Let me finish this first question first. We really do the real serum sample, and we can really catch the IgG antibody, and as I discuss with the medical people, they know the like COVID-19 infections. They have if you want to do the antibody treatment, the cost is very high, right? Because the antibody is very expensive. However, in our blood sample, in our serum, inside our body, okay, you have some bad antibodies. So people want to clean this first. Once they can catch all these kind of antibodies, so this kind of things is we are doing now. We can, as I can show you, right? I already show you, our antibody can catch, our neodymium can catch IgG antibody. So that means we can not only can catch IgG, but also so we inside the human body do the treatment. So this kind of things actually is quite interesting. We are doing now. And this kind of idea may be possible, or we are already doing. And the most challenging things is like human serum albumin. This is for strong interference. Okay, as a competition for the IgG antibody when you are doing the nanoparticle analysis. So this is another thing. But I think that the whole direction would be very interesting, and might be very useful in the future if one day we have a product for this. Okay, people can do this kind of a treatment. Okay, before the real diagnosis can really proceed. Okay, can proceed for this analysis. Okay, it's clear. Yeah.
Can we conclude, sir?
The second question I can give you my email.
We detect or analyze the cancer cells from Raman FTIR, and how?
Okay. Can we detect cancer cells?
Can we detect the cancer cells?
Actually, this is not the topic of my talk. Okay. Analyze the cancer cell from Raman FTIR. How? Well, okay. Cancer cell, okay. We can use our mass spec to measure the cancer cell. Okay, and actually, I have one publication we published in Atlanta, like 2011. We can measurement the cell endocytosis using cancer cell. It's a raw cancer cell, but Raman FTIR, I don't think it's easy to analyze. I don't know your target. What's the target compound you want to analyze here? We can measure the real cell mass, okay? But I don't know, Raman or FTIR is easy for that. Typically, it's not such easy things because Raman and FTIR so far for our surface scale validation, we know it's not such a straightforward things, and only know the ensemble things. You know what I mean, like a average effect, right? So it's not a really a very good tool to give a more precise information can be offered. You can plan for this. It's not easy and straightforward things. If this can be done, you will see a bunch of paper for that, right? But actually not, right? Okay, any questions?
Sir, if there is no any question, can we conclude the session?
Yeah, thank you. Yeah,
okay,
thank you.
Thank you very much.
Yeah, thank you. Bye-bye.
And we appreciate you because in very scheduled time you sharply joined virtually with us, and you also completed your talk in very sharp time. So once again, we all are very much thankful for your this accuracy. Okay, thank you, sir. Thank you.
Now we are reached to the next session. We have a second invited talk from Professor Mustafa Bosra from Department of National Research Center, Egypt. This session will be chaired by Professor C.J. Kamble sir. I request Professor C.J. Kamble sir to chair this session. Please, sir.
Respected resource person of this session, Professor Dr. M. Bosta sir, convener of this conference, Dr. G.J. Navathi, co-convener of this conference, Dr. Sumaya Madam, and dear participants from various colleges. Friends, I am here to introduce Professor Dr. M. Bosta sir. Dr. Bosta sir is a professor in solid state physics, Department of National Research Center, Egypt. He has received PhD degree at Göttingen University, Germany. He has extensive research experience in fabrication and characterization of thin films using various techniques. Professor Bosta has published many peer-reviewed articles in international journals. He is reviewer of many international journals. Today he is going to talk on metal oxide thin films, synthesis and applications. So I request Professor Dr. Bosta sir to deliver his lecture. Thank you.
Hello. Okay, can I start now? Okay, sir. Hello.
Hello,
Yes,
sir.
sir, it is audible. Hey, it is audible, sir.
Hello. Hello.
Hello.
Hello.
Hello, sir, it is audible, sir. No problem.
Okay. You hear me now, yeah? Okay. Good morning, everybody.
Good morning.
Yeah, first of all, I would like to thank Professor Patil about this invitation, and I thank everybody for this organize this conference. And I hope that I can speak with you about some little bit information about metal oxide thin film material. Okay. Okay, now? Did you hear me?
Yes, sir.
Okay.
Yes, sir.
Okay. Today, first of all, I am Dr. Mustafa Bosra from Egypt, from National Research Center. I will speak about metal oxide thin film material, and I will speak a little bit about this material and how to deposit and how to work with. Let me see how to present my work. How can change I have a problem with the presentation. I don't know how to move it. Okay. Sharing, sorry. Cancel.
Sir, you are not clearly audible.
I need
Hello,
to share my window, to share my talk. So it is the first time for me to use Google Meeting. So I don't know how to share, but I will do it. Maybe succeed this time. Okay. Did you see this sharing?
Yes, clearly, sir. No problem, sir.
Okay, it can change, yes? Okay.
Yeah, it can change now.
Okay. Today, I will speak a little bit about the metal oxide material, thin film, because this is my field and my interesting area. Today, I make some introduction for this material and techniques, how to prepare this material, and the type of the material. We have N-type oxides and B-type oxides, and how to deposit each of them. Some application of this material in our life and useful for us, and conclusion and acknowledgement. For the first of all, the metal oxide, we know that the oxides we have in our life, metal oxide and non-metal oxide. We have metal oxide, which is the metal material combined with oxygen, and the non-metal oxide is non-metallic material combined with oxygen. Metal oxide is interesting for a lot of application because it has a lot of form and powders in film 2D structure. Also has change in their electrical and magnetic and all properties according to the size and the position also. So we can use this material in different applications. If we go to the how to synthesize this material, we have techniques. As everybody knows that we have a physical techniques, and also we have chemical techniques. We have in the physical technique a lot of techniques everybody knows, but I didn't work in the physical technique. I use chemical techniques and chemical methods because it is very simple and very easy, and it is easy to set up the techniques. So I have in my lab especially spray pyrolysis technique, and now we add chemical bath deposition and also hydrothermal techniques. Spray pyrolysis technique, as everybody knows, that is a simple technique. We use an aqua solution with pressure air to atomize and spray the solution to a few droplets which drop in the surface of the hot substrate. This substrate heated by furnace or hot plate, and this spray droplets and the surface of the layer can be continuous to complete the layer of the thin layer or thin film according to the condition which we can optimize for each material and each thickness we need and each application we can use this material. Hydrothermal, everybody knows that is also simple way, the chemical technique is a simple way. You only put the material in the Teflon bottle and close it and put it in the oven for a long time, for maybe 1 day or 2 days, and after that you can get a thin layer or powder thin material. Chemical bath deposition is simple technique and is setting, and you can use it in each lab and it can be easy to work with. So I have prepared different materials. First of all, I start with titanium dioxide. Titanium dioxide, as everybody knows, is an important material in the photocatalytic area. And also we try to use it to deposit by spray pyrolysis. If you're looking before the deposition layers, we have many different temperatures for the spray pyrolysis technique to get a high quality material. And we found that the high temperature, about 500 degrees, we have a good crystallinity and a good material as this type and this temperature. According to the different concentration of the copper to the material, because we would like to add the copper to the titanium to improve its quality and also its efficiency in the photocatalyst, as we will see later. and we add a little bit amount of copper to the titanium dioxide material. And as you see, the transparency and the optical properties of the titanium not affected more by the adding of the copper, and also the surface of the titanium and the surface of the titanium doped copper is also have a small grain size, as we can see in the AFM measurement. After that, we use also to prepare the zinc oxide and zinc oxide doped magnesium thin film by spray pyrolysis. We add magnesium here for zinc oxide to use it as a photocatalyst also. We need to improve the and make movement of the energy band gap of the material. As we see here, the material, when we increase the magnesium oxide or magnesium additives to the zinc oxide, the crystallinity still go lower, and we lose the crystallinity of the material, but we didn't lose the small grain size of the surface, as we see in the scanning electron microscope, and we can see that the grain size with the magnesium started to be small, which is the key of the efficiency of the photocatalyst application, which we will see the data after that. After zinc oxide, we also prepare zinc oxide with some magnetic material, looks like iron, looks like nickel, and we have deposit the zinc oxide, pure zinc oxide, and we have also the dopant zinc oxide with the nickel and iron by spray pyrolysis. As we see, the crystallinity and quality of the material which we deposited is a little bit high, not bad, and it's very good. And we also have a good crystallinity in the special of the zinc oxide and zinc oxide doped iron with nickel. That's very fine grain size and small. And we also have published several papers on this material, as you can see in this part of the slide. Also, we work, as Dr. Patil mentioned, that the tungsten oxide is a very interesting material in electrochromic and a lot of applications, electrochemicals applications. So we try to deposit tungsten oxide by spray pyrolysis from different source material. As we can see here, 3 sources of material for deposition of tungsten oxide, and as we looking for, we have 3 quality or crystallinity different between the 3 sources of the material, but the crystallinity of all of them is almost closest to each other, and the grain surface is a little bit difference between the 3 source of material, as we can see in the scanning electron microscope. So we will see which one of this material can give us a good efficiency and performance in the application after that. After we finish this tungsten oxide by spray pyrolysis, we now try to deposit the tungsten oxide by hydrothermal application. Still work in this material, and we didn't complete the characterization of the material. We only make a Raman, and we confirm that this is the tungsten oxide. And also we have a scanning electron microscope. As we can see, there is a different surface structure, as we can see here, than the spray pyrolysis technique. This different structure appears in the surface material, in the surface of the material. It will lead us to a new application and a new use for this different structure. This is one of the advantages when you use 2 different techniques to deposit the material. And also, as we can say, the metal oxide, it is important for it how to deposit. Each technique can give you some advantages, and it can give you some different features and different structures that which can give you a few and a new application for the material. After that, we can deposit also in our lab a little bit some P-type material oxides, looks like copper, chromium, magnesium oxide. by spray pyrolysis. This material need a little bit, not in only spray directly. It need two steps to have a crystalline material, because when we deposited by spray pyrolysis, we have amorphous material, which is hard to know it is copper, chromium, magnesium oxide or not, but we make an annealing for this material at temperature close to 1000 degree to have this quality and has this high crystallinity materials. Also, we try to use it, and we try to make an annealing for this material for low temperature as about 600 degree, but we increase the time of the annealing. It's about 1 day or 4 days to anneal this material at 600 to have this crystallinity. And also, as if you look for the structure in the screen, in the scanning electron microscope, you can find that the grain size is increased and the crystallinity is more better than that in long time and low temperature. That is the quality of the material by spray pyrolysis and the annealing system. It is good for application in some way. Also, we deposit the copper iron oxides in film by spray pyrolysis. Also, this material is not easy to get it directly by spray pyrolysis, because we need to anneal this temperature, this material at high temperature. We anneal this material in special way at 800 degrees and 850 degrees and also 900 degrees. And we study the quality of the material, and we found that 850 degrees gives us a single phase of the lymphocytes material, but the other temperature, 800 and 900, give us combined by two phases, spinel and the lymphocyte phase. So we concern that, and we know that the 800 degree annealing for this layer give us a single phase of lymphocytes, which we're looking for at this moment for this material. Also, as we know that nickel oxide is one of the important materials. There's a lot of applications because it have a lot of advantages. We deposit the nickel oxide by spray pyrolysis through the three different sources: acetate, chloride, nitrate for nickel material as a source of material. So we deposit these three materials, these three resources material, and we found that we have a different quality of the thin film from X-ray and also from scanning electron microscope. We have a different service structure built from these three different sources. And also the energy band gave a little bit difference according to the source of the material which we used in the spray material as a starting material. So we can know that which service of these materials and which source of these resources can be used for us in the application and in the different application according to the structure of the surface of this material and according to the energy band gap of the nickel oxide layer which we have. When we deposit the nickel oxide by chemical path deposition, you can see that there is also different in the comparison, but also as we know that the chemical path deposition, it is hard to have a nickel oxide layer directly by the chemical path. But we start with the nickel hydroxide layer, as we see here, and after that we can make an annealing for different temperature. According to the temperature, we can find the nickel oxide phase. As we can see here, we make an annealing at 450 degrees for about 9 hours. We found that we have clear and only phase of the nickel oxide material. If we look for the structure service of the material according by scanning electron microscope, we can see that we have flex structure which we didn't found in by spray pyrolysis. This flex gives us a surface area, different surface area, different surface quality, which can give us different application and different performance for the material. And when we use it in the application, as we can see, that is the flex is clear here, is totally different than the spray pyrolysis which we have before. If we come to the part of the application, as we can see here, there is a lot of application for the material, for metal oxide material, but because metal oxide material, as we know, that's the key factor and the key point of this material is the surface and also the size of the grain size, which we can reduce it to the nanoscale. And when we reduce it to the nanoscale, so we can increase the surface area, which is active, which it can be make performance for the material and increase the application of the material. So the metal oxide material is a lot of application can be used for this material, as we can see in the photocatalyst, in the gas sensors, the batteries, supercapacitors, solar cell, anti-corrosion, antibacterials, a lot of applications we can use this metal oxide on it. So I concern in 2 or 3 items only for this application of this material in my lab and my also cooperation with the people outside of Egypt. So I start with the photocatalyst. Everybody knows that the photocatalyst material, the ideal material for the photocatalyst is the titanium dioxide. So start with the titanium dioxide to check if spray pyrolysis technique deposit titanium oxide and titanium oxide doped cover can be used for the photocatalytic material as a photocatalytic material and give us some efficiency and some result. So I use the titanium oxide with the crystal violet dyes, and we can see that with the different time the catalyst can affect on the dyes and the decrease of the absorption age of the material. And also the copper, when we add the copper to the titanium dioxide, it gives us also more efficiency and more decaying for the dyes in the solution. And we conclude all this efficiency in this graph, as you can see, when we add the copper to the titanium dioxide, the efficiency and the performance of the material can be increased and improve, and we can get a lot of decaying in the dye inside the material, because dye, as everybody knows, is unpolluted chemicals for some output of the industry, looks like textile, looks like some chemicals company. So we need to clean the area from this dyes, so we can use this material, titanium dioxide, in the form of thin layer. Most of the people in this area use the titanium oxide and titanium oxide in the powder form, which is not easy to collect again from the solution and from the chemicals. But thin layer, it's easy to add to the solution and also to remove from the solution, which is easy and make it simple way for the photocatalytic. So that's one of the advantages of the thin layer of the material used in the photocatalytic area. Also, we use zinc oxide and zinc oxide doped magnesium, because all people looking for the another alternative material for the titanium oxide in the application of the photocatalyst. So the people suggested that the zinc oxide is one of this material, but we need to improve the quality and also improve the performance of the zinc oxide. So we added the magnesium oxide to the zinc oxide to move the energy banding gap a little bit to the UV direction and make it a little bit wide banding gap, which can absorb more UV light and also give us some improve in the quality. If we're looking here for the zinc oxide, the absorption and decay of the dyes is not a little bit high, but when we add the magnesium here for the zinc oxide, the increase of the absorption and the decay of the dye inside the solution. And we conclude everything here. We can see the difference between zinc oxide and 3% of 0.3 or 3% of the magnesium oxide added to the zinc. The difference is a little bit high, and we can be considered a good material for the photocatalytic application and the decaying of some dyes in the chemical solutions. Also, nickel oxide, we can try to use nickel oxide as a photocatalytic material for some dyes also, but in this way we can use it as two layers. We deposit nickel oxide, and on the surface of the nickel oxide we add a zinc oxide layer, but zinc oxide layer here deposited by CVD, chemical vapor deposition, not by spray pyrolysis. So we can test this material, and as we can see the zinc oxide and the two different thickness of layers of zinc oxide, and we can see that the lower thickness of the zinc oxide layer on the surface of nickel oxide gives us more decay than the layer when the thickness of zinc oxide is a thick layer on the surface of the nickel oxide for the photocatalytic application and for the dye cleaning from the solution, as we can see here from this curve. So we can use on the photocatalytic area, we can use P-type material also, looks like nickel oxide, or N-type material looks like zinc oxide and titanium oxide material for photocatalytic application to clean our area from these dyes. After that, we can looking for some also chemical catalytic tungsten oxide, because tungsten oxide, it can be also to clean or to formation for nitrophenol for phenol to clean it from the area also and from the solution, because this is also toxic dyes, and we can change it and clean it from the area by using the tungsten oxide thin film, which is deposited in our lab, and we can compare between the three different sources which we use it for deposition of the tungsten oxide by spray pyrolysis. We can see that this one is ammonia metatungsten layer. It gives us some more details and more decaying for this material and more change from the toxic material to untoxic material when we use this material, better than the two resources, different resources of the deposition of the tungsten oxide material. After that, we can have also the second application for this material, and the common application for the metal oxide material is the gas sensor application. As we know, the pollution of the area of the air in everywhere is a lot of people, a lot of country suffer from the pollution of air in the city and the big city especially. So we try to use this metal oxide to sense and to know and to give us some information about the pollution of the material or pollution of our air which we are living. So I start with the tin oxide and tin oxide of palladium material. We use this small technique for measurement of the gas sensor material for the carbon monoxide, and as we can see when we add the palladium to the tin oxide material, the efficiency and the gas sensor is increased, and also this material can sense with this polluted carbon monoxide material at low temperature is about 150 degrees. It is low temperature for this material, and we can measure the gas pollution, and we can know that there is exist of the carbon monoxide in the area which we live in. Also, we use the nickel oxide material for NO gases, natural nitrogen oxide gases. As we can see, this measurement is done in Sweden University, Linköping, when my PhD student were there, and you can measure the ammonia solution, ammonia gases as a detection by nickel oxide. As we can see, the dynamic of the detection of the nickel oxide material with the ammonia, and we have different material the thickness, and we can see that the sensitivity increase when the thickness is very low, and also the temperature is not high, the most towards 200 degree, and also we check the nickel oxide, this nickel oxide layer deposited by spray pyrolysis with different gases, and we can see, sorry, and it is, I make a mistake. This material, this is not measured in Sweden. This is measured in India with Professor Patil. Sorry for that. for that. This is measured in India with Professor Patil in Kolhapur and Jivaji University, and they measure this sensitivity for our sample, and also they tested the sensitivity of this sample for a lot of gases, but we found that the nickel nitrogen oxide is the highest one for this layer of the material, and also they check the stability of the material, and we found that is about 20 or more than 20 days the material is still stable and gives the same sensitivity and the same performance. Also, this material of nickel oxide, we check it in Sweden for ammonia gases, and we can use the material of nickel oxide which is deposited by chemical bath deposition, and also deposited by 3 different material sources by spray pyrolysis, chloride or acetate or nitrate, and we can conclude the sensitivity of this material. We can find that the chemical bath deposition material is the highest one, because the surface of this material, as we saw before, is flex surface, and the surface area of this material deposited by chemical bath deposition is totally different than the surface area and surface structure for the material deposited by spray pyrolysis. So this surface area is the key in this application. So the material deposited by chemical bath deposition is better than, and the gas sensitivity than the material deposited by spray pyrolysis. So we can say that when you try to use the material for some application, you're looking for the good and which technique can give you some advantages for this material for this application. Looks like we did here in this in this material. We checked 2 techniques, and we found that the chemical bath deposition is better than the spray pyrolysis for the gas application, for ammonia application, ammonia gas application as a gas sensor. Also, we try to use this as a PN and diode structure, because it's optoelectronics materials. They also can use it in the diode, and also can use it in the solar cell application. We also work in this area, but there is no time to represent some application of this material in the solar cell area. So also we make a nickel oxide as a dilute here, as you can see, and we make a rectifying for the curve, and we can see that the nickel oxide, when we introduce it here between zinc oxide and silicon material, the rectifying effect is better than the before. So I think this material also can use in the diode, or in the performance, increase the performance of some diode and some solar cell application and photovoltaic application. Conclusion, we can say that the chemical techniques which we are using is spray pyrolysis, chemical bath deposition, hydrothermal deposition technique are very promising technique for some application, for because each one of them with surface structure different for the material when deposited by. So we can use each technique for some application better than the other technique, as we saw before. The chemical bath is better than the spray pyrolysis in the applications of the material. So also in our lab, we concern our work in the metal oxide material, looks like zinc oxide, titanium oxide, nickel oxide, tungsten, and some P-type like nickel oxide and copper, chromium, copper, iron oxides. Also PV materials, we work in this area, as Professor Patil mentioned, that we cooperate with them in some of these materials, and we still work in this area also, copper-based material for solar cell application and photovoltaic application. And we're still interested in the application in the area of the photocatalyst and the gas sensor for our materials which we are deposited in our lab. So we cooperate with a lot of people, and I would like to thank a lot of our partner outside of Egypt, especially Dr. Catherine from France, and Dr. Mauritius from Italy, and Dr. Patil from India, and also Dr. Rositsa from Sweden, and Dr. Jan from Poland. All of them give me a lot of information and help me in my career, and help my students also to study and do some good work in their lab and their facility. So I would like to thank all of them about this opportunity. They give it for me and for my colleagues in our lab. And also I would like to thank my group and my team, Dr. Muhammad Saeed and Dr. Muhammad Goma and Dr. Hagar Muhammad and Mrs. Ola. She is a PhD student until now, but will finish soon. Thank you very much. I would like to thank you everybody for this opportunity, and to have thank you for your attention, and I can open the discussion if there is some question. Thank you very much.
On metal oxide thin films, synthesis and applications. Hello?
Hello, yeah.
Thanks, sir, for giving a nice lecture on metal oxide thin films, synthesis and applications. Now topic is open to discussion, so I request all the participants, if they have any questions, please ask the questions or write in chat box.
Hello, sir. It was very nice lecture that you delivered. One question is that is there ball milling processes available in your laboratory, sir?
I have spray pyrolysis, hydrothermal, and the chemical bus deposition in my lab.
Yeah, because in the slide you mentioned this process. So
Yeah, I have three of these techniques in my lab, and I can deposit metal oxide material by these techniques. All of them is the chemical techniques. And it's simple to set up, and you know that it's simple to set up of this material, and it's also low cost techniques to deposit the high quality material. That is the interesting point of us in these techniques.
Hello, sir.
Hello?
In one of IV characteristic, I have seen that the PN junction diode sees a negative current in a fourth quadrant. Why it is due to?
You know, it is sometimes is due to the quality of the layer of the deposited sample. Because when we deposited the nickel oxide on the top of silicon with the temperature, so there is a few layer of silicon dioxide is a little bit appear. That's which makes some a little bit high resistance for this point. So the quality of the deposition. So we need to work on this area more and more to improve this problem.
Thank you, sir.
Okay.
That nature is same for all materials. Hello, sir.
Yes, sir.
Is that nature of that graph is the same for all materials?
Sorry? Which,
is that the nature of that graph, IV characteristic nature, is same for all materials?
Nickel? I didn't hear. Please, can repeat the questions again? Please, I didn't hear well.
Question. Sir, there is a question for you. Sir, a glass deposited with metal oxide will be able to neutralize high power laser beam and save eyes from permanent blindness.
I don't know exactly which material we can deposit it on the glass to prevent laser power from our eyes. That is the point. Because laser need special material, so I don't know exactly which material we can deposit on the glass. Okay. Is it okay?
So shall we conclude, sir?
Sorry?
Hello, sir.
If there is no any question, shall we conclude?
Hello.
Hello?
Yeah.
Yes,
Bosta, sir.
Yes, Patil, sir. Ask your question.
Yes, sir. Thank you, madam. Sir, I am asking you that if thin film, if metal oxide thin film or composite material, is there roughness affects the properties of gas sensing?
Yeah, as we can see that the surface is a key point of this material in the application of the gas sensor, especially because in the gas sensor we need a big surface area. So as I present in my presentation, the nickel oxide deposited by chemical bus deposition, which have flex structure, means the surface area, large surface area, is better than the material that deposited by spray pyrolysis, which doesn't have this large surface area. So roughness is important in some way, but in the limited, not a high roughness, because if you have a high roughness surface, this means this material is not be stable for a long time and long application. So
Okay.
you need surface for limited surface roughness, because surface roughness is important in some application.
Okay, sir.
Okay.
Yes, thank you, sir.
Thank you.
Sir, can we conclude now?
I hear you.
I think there is no questions.
Okay. No, I'm lucky.
Okay. Thanks again, sir, for giving valuable time for this conference. So once again, thanks you.
Thank you very much. Okay. Bye-bye.
Karantkar sir.
बोला सर.
Can we start the third session immediately?
Yes, because the resource person is there.
Yes.
So
Okay, all participants are here. I informed that immediately we start the next session. The chairperson for next session is Dr. S.I. Inamdar Madam. I request Dr. S.I. Inamdar Madam, immediately you start the next session.
Thank you, sir. For this session, we have with us Dr. Mengdui. He's from University of New South Wales, Australia, Sydney, Australia. I briefly introduce to Dr. Mengdui. He is currently a postdoctoral researcher at the School of Photovoltaic and Renewable Energy Engineering, University of New South Wales, Australia. Dr. Mengdui has received his BS and MS degree in Material Science and Engineering at Chongnam National University, Korea in 2015 and 2017, and PhD degree from UNSW in 2021. So far, he has published 8 research articles as the first author in peer-reviewed journals like Advanced Energy Materials, Advanced Functional Materials, Advanced Sciences, etc. His research interests are earth abundant materials for application in photovoltaic devices and solar hydrogen evolution. After this brief introduction of Dr. Mengri, I request to Dr. Mengri to start your lecture. Please,
okay.
sir.
Yeah. Good afternoon. Can you hear me clearly? Yeah. So I'm Mingri from the University of New South Wales. So thanks for the community to provide this chance for me, and I can present my work in this e-conference. So today's my topic is about defect engineering in castorized thin film solar cells. So many of you might already know what is castorized. So it's copper zinc tin sulfide or selenide inorganic compound materials. This P-type materials can be used as a solar cell application. So my group is meaning doing the developing the castorized thin film for the solar cell application. So today I would like to introduce my field works, my PhD works. So here is a content. So first is a background, and second is shallow defects engineering, and the next should be the deep defects engineering and the conclusion. So let's go for the background. So actually, I don't know whether many of the tendency is from the material science or the physical science. So because of my project or my research topic is related to the solar cell, so many of you might not well known about the thin film of the solar cell. So I would like to introduce a little bit background about the thin film solar cell, especially the thin film solar cells. So here is the market share in the Germany for the different materials for the solar cell application. As you can see, there is polocrystalline silicon, monocrystalline silicon, and copper indium gallium selenide, and cadmium telluride, and other things. So in the market, many of the market was shared by the silicon solar cell, while the copper indium gallium selenide and the cadmium selenide shares a small part in the market, around 5%. So why this 5% of the thin film is still required for the future developing? So this is because the thin film solar cell has many advantages, such like the lightweight, and it can be the flexible, deposited on the flexible substrate, and it has much better performance in the wake light, and it has definitely has a long time lifetime because they are all of the inorganic materials. So it comes to the one of application like the IoT application. So we can use a thin film as a powered sensor for the IoT application. So I guess this would be the one of the future research direction for the thin film solar cells. So for the there are lots of companies who are doing the thin film solar cells, such as CIGS and cadmium telluride. So most of companies, they are from China, and some are from the United States, and a few belong to the European group. So as we can see, the thin film solar cell is still promising for the market. So in the future, I believe the thin film solar cell should share the more the photovoltaic market in the near future. So except to the materials I mentioned here, like CIGS and cadmium chloride. So there is another materials called chisteroid materials, which is a copper zinc tin sulfur selenide compound. So this compound actually enjoys also abundant and low or non-toxic toxic advantage. So because the selenide has a little bit toxic, so few of group are remove the selenide, and they are doing only doing the pure sulfide CDTS. So our group initially we was only focusing on the pure sulfide CDTS, but recently we have also developed the selenide content, the chisteroid solar cell. So to move on the chisteroid crystal structure, actually the chisteroid is derived from the zinc sulfide structure. The zinc sulfide, the one zinc can be divided into the copper and the indium. So the copper indium sulfide is kind of the second generation for the zinc sulfide materials. So after that, if we divide the indium to the zinc to the tin, so we will come to the copper zinc tin sulfide. So basically, the CDTS crystal structure is similar to the copper indium sulfide structure. So why we're doing the CDTS solar cells? Because CDTS, as I mentioned, it enjoys the Earth abundant, so it's only like copper, zinc, and tin. They are super cheap. So once the CDTS approach like similar efficiency compared with CIGS or cadmium chloride, like around 20%, their cost of the this type of solar cell we only the 20% of the CIGS materials cost. So it is much worth to do it because they had the low cost advantage. So let's take a look at the efficiency chart, how the CDTS located in the all of materials. So here, actually, the CDTS currently record certified the record efficiency for the CDT SSE solar cell is only 30%. So this efficiency just achieved in the last year by the Chinese group. So before that, actually the CDT SSE solar cells has been not improved a lot during the 1 decade because of few of the crystal defects I will mention in the later. So compared with the other types of solar cell, as many of you know, the perovskite solar cell, they already achieve the high performance, which made by the units from the Korea. So they already got 25%. So it's amazing efficiency, and it could be promising for the next generation solar cell. However, compared with our CDTS solar cell, so to commercialize the perovskite solar cell, we have to figure out two problems. One is the stability issues. Maybe many of you already know. So the perovskite materials, it's organic and inorganic halide materials. So the stability is a little bit problem. So so far the highest stability was reported around 2,000 hours, I think. So this is the first problem for the perovskite, the stability. Another problem is if we want to scale up the perovskite solar cell, like make the production line, so we have to find a suitable deposition method. As currently the highest efficiency is made by the solution method, which will decrease a lot about their efficiency if the size of solar cell increase a lot. So this is a true problem of the perovskite solar cell. One is the stability issue, and another is the scalability. So compared with perovskite, the CCTS, because CCTS is inorganic materials, so it has a very good stability. And the CCTS, the device structure of the CCTS is quite similar to the commercialized CIGS solar cell. So I believe if the CCTS can achieve the much better efficiency, it can be easily scale up for the commercialization. So this is a true advantage of the CCTS solar cell compared with the perovskite. But however, the CCTS solar cell still has a very low efficiency. So other promising materials for the solar cell application, like organic materials, quite interesting. The organic materials actually, I think 5 or 6 years before, it also stayed at the 15% efficiency. But recently, the efficiency of organic materials, organic solar cell, has been boosted a lot. So as you can see, the certified efficiency already 18 something. So this might be another hot topic in the maybe 5 or 10 years. So besides all of single junction solar cell, there is another way to develop to much higher efficiency, which we call it a Tendon solar cell. Simply, it's connected two different solar cell, two different band gap solar cell together. So, for example, here we can see the HZB achieved near the 30% efficiency by combining the silicon solar cell with perovskite. So it is also quite promising. So we have pay attention on it, and it might be changed in the world future. So again, I would like to emphasize the advantage of CCTS. Although it has a low efficiency compared with other materials, but the stability and upscale, it's CCTS. It's one of two of the advantage of CCTS solar cells. So let's take a look on the progress of a castorized thin film CCTS in the USW, what we did. So actually we choose water record efficiency, certified water record efficiency for the pure sulfide CCTS solar cell. So we achieved this efficiency property in the 2019. So it's certified 11% for the small area and the 1 cm. For the larger area, it's around 10%. So we published this article in the Nature Energy. So we continuously do the different optimization. So from the initially, we do the composition optimization, change the ratio of copper to zinc or copper to the zinc plus tin. So we second, we control the sulfurization, which is the formation of the how we can formate the CCTS materials. So, I'm sorry. The Kumar mute his mic. So next we optimize the buffer. We replace the different buffer.
Very sorry, sir.
We replace different buffer, and finally we use the heterojunction treatment to enable the CCTS solar cell to reach the water record. So another one is we also did a little bit research on the pure selenide CDTS also. So we have achieved also a certified efficiency around 12.5 in 2020. Yeah. So here we can see like we almost achieve a same VOC value compared with the copper Indian selenide. So and we also get the lowest VOC deficit. The low VOC deficit is one for a key issue for the Castor motors. So we did a pretty good job in the both motors. So let's change to the topic today. So what is the problem for the Castor thin film? So why it cannot go to much higher efficiency? So here the main problem for the Castor thin film is the Castor bulk materials. So actually there is two kind of problem. One is narrow phase formation region, and another is low formation energy for different defects in Castor, which is related to our today's topic. So first one, the narrow phase formation region. As you can see from this diagram, so because we want to form the CDTS pure CDTS phase like copper 2, zinc, tin, and sulfur 4. So actually, it is quite difficult to form this kind of phase. As we can see, if the composition turning a little bit, we can easily get some of a second phase, like copper sulfide, zinc sulfide, or some other terminal phase, copper zinc sulfide, copper tin sulfide. So we have this is the first problem we need to take a look. Fortunately, this won't be too difficult to control. Once we get a good composition region, like we optimize the composition, so and the earning and condition for the formation of CDTS. So normally we can get the highly crystallized pure CDTS phase with less secondary phase. So this is okay so far. And however, because of the materials of nature of the materials of CDTS, it is quite easily to form the different defects. As we can see from here, so we can form various defects, but also some defects cluster. Some of the defects are good, some of the defects can be very bad. So, for example, so the shallow defects, like here, the shallow defects should be the copper vaccine and copper zinc anti-side defects. So in CDTS Castor motors, these two defects actually contribute to the p-tap conductivity. So if we get much more of these defects, so our the motors CDTS motors can be improved a lot. So this is one of my topic today. So I did some the engineering about the shallow defects. So which I changed copper zinc tin anti-side defect to another defect. In addition, I would like to mention one of things like in here the shallow defects, copper vaccine and copper zinc tin anti-side. Normally, it is quite difficult to get the copper vaccine defects because the formation of this defect is a little bit higher than the copper zinc anti-side defect. So yeah, so if we have some method to form this kind of defect, it might be also good for the Castor motors. So on the other hand, the one for bad defect like deep defects. So for example, like middle bank defects like tin vaccine defects or some tin zinc anti-static defects, it can act as a charge recombination center to limit the efficiency. So here's also our task to resolve this problem. So here is my methods, background for my method, how I going to change the defects of in the CDTS bulk material. So actually, one of the way to change the defects is doping or allowing the new elements into the castoral materials. So if we doping, we can easily change some of the property, as you can see here, the definition of the doping. And if we allowing something, we can change some mismatch between the lattice that will be also reduce some formation energy of some of the defect. So that's my strategy. So as we have a copper zinc tin, so we have many choice to replace this elements. For example, for the copper, we can allow the silver or doping the lithium. For the zinc, we can allow the cadmium and other things. For the tin, and we can allowing or doping the germanium. So actually, in the CDTS, the silver, cadmium, and germanium are the most popular materials that can be incorporated into the castor bulk. So today, I would like to introduce my method about I did the lithium doping. This is the first topic for the shallow defect engineering. And for the deep defect engineering, I allow the cadmium and doping the germanium together. So before start my topic today, I would like to introduce what is the device structure looks like for the castoral source. So the back contact is normally it's a molecular site. So and here's the castoral absorber and the buffer layer, N-type buffer layer, and we use the IQAC side and the TCO like ITO and AZO we can use, and we deposit the metal contact for the working for the at the solar cells. So here is the first work for the shallow defect engineering. So actually, I won't go the much details for both of work. So I will just introduce the key point of my work. So yeah. So here it's a shallow defects engineering for the CDTS. So once we get the CDTS absorber by salinization, so I prepare the lithium chloride solution for the doping the lithium. So what I did is I put some lithium chloride powder in the DI water, and I heat this solution to the 80 degree on the hot plate, and keep the warm for the like 1 hour. And after that, I soaking the CDTS materials for the doping. So once I dope the lithium, so the lithium elements will go to the bulk, and some will go to the green boundary of the CDTS. And first, I check the top thickness. So it's one of the characterization that we can know where the elements are located. So as we can see, the left one is reference one. So and the right one is the one I did the lithium doping. So obviously we can see the strong signal of lithium, and on the left side we almost cannot observe the lithium. And after that, we did the APT, that can observe the atom size scale, how the elements are located. So here we observe the lithium, which is located all of the bulk materials of the CDTS, no pattern in the green and green bottom. So, but the lithium concentration is quite low. So once we confirm the lithium is in the bulk materials of the castoreum, so we measure the IV curve, like device performance. So we can observe the efficiency of the CDTS has been improved. So the VOC, JSC, and the fill factor, which is three parameters that can determine the efficiency of the solar cells. So after that, so we characterize the conductivity of the CDTS film by DRCP. So we found that the conductivity, P-type conductivity, has been improved after lithium doping. As you can see, not all one order, but it increased a lot for the doping density. So here we need to know why it can be improved. So here we characterize the AS. So the AS is one for characterization that we can detect what kind of defects that our materials have. So here we did the AS, and after fitting this result, we get the activation energy that will collaborate with the defects tab. So as we can see, the activation energy of the CDTS-SE without doping, it shows around 120, which is corresponding to the copper zinc anti-side defect. And after doping the lithium, so it's reduced to the 19 something. So, and we can confirm the doping also increased by the AS as well. So the shallow defect has been changed after the doping lithium. So, but we don't know why, what is, so according to the literature, and they did some DFT calculation, so we know, so if we get the activation energy around 100 something or 120 something, it is corresponding to the copper zinc anti-side defect. So we don't know what is defects for the activation energy around 90 something. So what we did is we did some DFT calculation. So according to the DFT calculation, so the lithium zinc anti-side defect is around 0.09. So which is quite agree with the one we measured is 19.2. So we can strongly conclude that the shallow defects in our materials has been changed. So about the deep defects engineering, so here actually the castoreum materials, as I mentioned before, the efficiency of castoreum materials has been limited by the non-radiative recombination, but it's at the different region actually. So one is in the interface and another is in the bulk. So both region has limited some property of the castoreum materials. I will not emphasize here. So here I would like to mention how I did this doping and alloying experiment. Because in here, this experiment, I did the cadmium alloy and germanium doping. So first, I made the copper zinc tin precursor by spotter. After that, I pre-treat this precursor by a pre-alloying process. So this process will enable the precursor become to the alloyed phases. Before it's just a stack order. So after that, I put the one thing germanium layer in here as a germanium source by spotter as well. So after that, I deposit the cadmium sulfide as a source of cadmium for around 10 nanometer. So here is a structure of my precursor. After that, this precursor will undergo to the sulfur cylindrization at high temperature within in the sulfur and cylinder atmosphere. After that, I can go to the CDTS SE absorber with doping germanium and alloying cadmium. So I did following the procedure about CDS, window layer, and the metal contact. So first one, I did of course I checked confirm whether I successfully incorporate both materials, germanium and cadmium. So as we can observe that there is like a weak signal of cadmium. So we calculate it's around 5 atomic percentage. So yeah, we did successful on the cadmium alloying. So after that, but unfortunately, we cannot observe any germanium. But it is highly due to the resolution of the TEM, because I also did the same thing here, but I'm not showing I didn't put the figure in here. So we found the germanium signal in the same, so which also means we also incorporate the germanium as well. So after that same, I did made the device. So as we can see, like compared with the reference one, without any like doping on the alloying, it only shows 8%. But after doping the germanium and alloying the cadmium, the VOC GSC fill factor 3 parameter have been improved. So which contributing the final device performance. So here I would like to go directly about the deep defect engineer. So similarly, I did the AS in here to characterize the what kind of defects we had in our materials. So as here we from the data we can get 2 different defects level. One is a shallow level defect, N1, and another is deep level defects, N2. So the shallow level in here should be related to the copper zinc anti-side defects, as I mentioned before. So another one, deep defects, we don't know, but it should be related to some tin related deep defects. But fortunately, after doping the cadmium, allowing the cadmium and doping the germanium, the defects level have been reduced a lot. Means in here, I plot some figures. So the defect level, without doping, we have many different deep defect level that can act as a recombination center that limit the efficiency. After that, the deep defect level was reduced, so we got less recombination in these films. That shows a higher performance. So here is a conclusion. Like the one is first is lithium doping. So we confirm that lead dope can change the shallow defects. So which improve the PDAP conductivity that we published this paper in AM, and another one is double pentane incorporation, germanium and cadmium. So probably you can take a look on this paper in the AFM. So here I would like to thank my supervisor, Professor Xiaojing Kang, and Professor Martin Green, and Dr. Genji, and another Professor Jin Hao King. Maybe many of people already know in Shivaji. So actually, he hosts many of students from the Shivaji University, and I also graduated from his lab for my master. So he's a very kind of a professor, and I encourage you to go their lab. Their lab facility is amazing, so you can do a very good job in there. So thanks for your attention. So any question? So yeah, thank you. Yeah, probably you mute yourself, I guess. Probably you mute yourself. I cannot hear you actually. Hello?
Hello.
Yeah. I think
Yeah,
Dr.
I will communicate to my.
Say something, but I didn't hear anything from her. Yeah.
Just moment, sir.
Yeah, sure.
Yeah, mic of anchor is off. I will communicate.
Yes.
Yeah.
Yes,
Yeah,
extremely
I can
sorry.
hear you. Yeah, I can
Yes,
hear
yes.
you. Yeah.
Dr. Mingdui sir has nicely explained the solar cell based on heterojunction defect system. Now this session is open for the discussion. Those who have a question, unmute your mic and ask the question, or you can ask your question in a chat box also.
So,
Is there any
actually,
question?
yeah,
Please
yeah.
ask your question.
Yeah, so actually I didn't go much deeper today, so because so I saw the title of this conference is basically based on the nano materials. So yeah, so probably yeah, I just because I'm doing the solar cell, so yeah.
Hello, sir.
Yeah, hello.
I have one question, sir. In case of solar cell, there is a problem of efficiency, and well-known solar cell is a silicon solar cell. So can we replace the silicon solar cell by casterite thin film solar cell?
Yeah, actually, yeah, very good question. Yeah, actually, this is also a question before I started to the CDTS. So I'm wondering why we're doing the CDTS. Can the CDTS compete to the silicon solar cell? The answer is no. So we cannot compete with the silicon solar cell. So as you already know, like silicon solar cell is already dominant in the PV market. So and the silicon solar cell, the chip of the cost of a silicon solar cell is already low enough. So if we consider about price, probably yeah, CDTS doesn't have any advantage for the rather than the silicon solar cell. But on the other hand, the silicon solar cell cannot be used as here I mentioned like a flexible solar cell. So the reason why we're doing the thin film is because we want to apply it into the flexible substrate, and the CDTS has a much better performance in the weak light. Like for example, in our room, like in the house, so we probably can assemble some CDTS solar cell as IoT production, so we can power that. So I mean the two let me summarize my conclusion. This is the two reasons. One, we can, like CDTS, can deposit in the flexible substrate that is advanced than the silicon, and it has a much better performance in the weak light that silicon doesn't demonstrate that ability. So yeah, so for the general market, I would like to say like CDTS cannot compete to the silicon solar cell, but on the other hand, in some of cases, CDTS might be much advanced than the silicon. That's my answer.
Thank you, sir.
Thank you, sir. Sir, we have one more question from Bobde, sir. What is the maximum efficiency of solar cell that you synthesized in your lab?
So currently, like what I said, so the CDTS materials has pure sulfide or pure selenide or mixed sulfide selenide. So currently, the baseline of pure sulfide, so without selenide, we can achieve beyond 10%. So with higher VOC, around 800 milliwatt, and that's why we didn't publish that paper so far. So this is pure sulfide. For the pure selenide, our baseline is around 11 something. So sometimes we can achieve beyond 12%. For the selenide, sulfide and selenide one, we haven't exactly started that experiment yet. So maybe probably we can also achieve beyond 11, but like between 11 to 12, definitely we can achieve. Yeah. So I guess our lab has achieved a very good performance for the CDTS solar cell in all of the world. Yeah. So let me take the second question. So can we decrease deep defect to increase the efficiency of lithium? Okay, so the question is, can we decrease deep defects to increase the efficiency of lithium solar cell? Yes, of course, we
Yes.
can. We can, but I haven't tried it yet because actually this work is related to my PhD topic. So my PhD topic is about doping effects of the influence of doping and alloying. So I needed to figure out what is like a single effect of the lithium or single effect of cadmium, single effect of the germanium. So I haven't combined all of the together, but from our results, probably we can. Yeah, but we have to give it a try on that. Yeah. Thank you. So the next question is, by using your method, can we reduce the toxicity of solar cell after they become incorporated? For the toxic issue, I guess in here, as you can see, like cadmium is heavy metal, so probably, yeah, because I just did, like, you can consider this is a basic science. We just explore what is the true effect of the cadmium. So actually in this paper, I also demonstrate influence of a single incorporation only cadmium. So probably I would not recommend to like incorporate the cadmium in the further future, because it will be like contradict to the materials, like, because CDTS of it enjoys the eco-friendly. So if we dope another toxic materials, probably it's not good idea. So yeah. So I don't think the toxic issue will be reduced. Yeah. If I didn't misunderstand your question. Yeah. Yeah. Okay. So the next question is, many group has report improvements in the efficiency after doping, but there are reference efficiency around 10%. If efficiency of a reference efficiency is near the 12%, then after doping, do you think it will increase? Very good question for this one. So actually, what we observed is like when the reference efficiency will go a little bit high, like for example, your reference shows like 10 or 11. So based on that efficiency, if you dope something, like you dope the germanium, you dope the cadmium, actually the improvement of efficiency will be less, and sometimes will also decrease efficiency. Yeah, this is like the one we need to explore. But fortunately, as I show in here, so the one of Chinese group has reported 30% efficiency. Actually, this one is achieved by the silver alloy. So which means they had a very good baseline, but even after alloying the new elements, the efficiency still goes high. So what I believe that the doping or the alloying still is promising, but we need to find a suitable method to, like, for example, the processing temperature and what is this like doping materials located, and how we can use these materials in the future. So what I believe is like the doping and alloying still can improve the CCTS performance in the future. Yeah. Okay. Yeah. Yeah. Okay. So if I didn't answer your question clearly, so you may like leave your message in the chat box. I will like explain more. Yeah. Yeah. Okay. Hello, sir. Please explain again how shallow defects level change after doping of lithium. Okay. So probably I go little bit hurry on this part. So so first, after we doping the lithium, so the first things we checked that our conductivity was improved. So when the some property like electro property has been changed, so normally it's related to the some defect was changed. So following that, we calculate the how the defect in the film has been changed by the AS measurement. So here, so we get the capacitance. So after fitting this curve, we can get two levels, one defect from each sample. So here, the reference one without lithium, it shows the shallow defects, which is corresponding to the copper zinc anti-side defects. Here, copper zinc anti-side. This is calculated by the calculated by the DFT. So we know this is a copper zinc anti-side defect. So after doping the lithium, it has been changed and to the more shallow defects. So which are around 90 something. So, but we don't know. There's no any literature or calculation around if the one defect is getting this kind of a lower level. So which defect it is. So after that, we use the defect DFT calculation. Similar in here, you can see this diagram is similar in here. Okay. So we calculate. So we found that theoretically, the lithium zinc anti-side defect. So the transition energy means the activation energy is around 90 something. So which well agreeing with the one we measure in here. So we confirm that this should be, and this highly likely belong to the lithium zinc anti-sag defect. So that's we conclude in that paper. So yeah.
Thank you so much. Is there any question from you participants? If there is no question, we conclude this session. In this session, all the participants has actively participated. So thank you so much to all participants for your active participation in our conference. Thank you so much, Dr. Mengdui sir, for delivering nice lecture on solar cell. Thank you so much. With the permission of President, I declare that this session is over. There is some announcement for the participants. Next session of this conference is the poster presentation. That session we will start on 2 p.m. So those participants are participating or presenting posters in the conference. Please be ready at 2 o'clock. We will start on 2 o'clock. Here I display the poster presentation schedule on the screen, and we will sharply start our poster presentation on 2 o'clock. Thank you so much.
How did it? I like